Hey guys, I've been given an interesting projectile motion question today to look at. So the question says a basketball player successfully shoots a goal from a horizontal distance of 5.3 meters to the center of the hoop. He releases the ball at an angle of 48 degrees to the horizontal and 1.2 meters below the height of the ring. What is the ball's speed the moment it leaves the player's hands? Okay, so this is going to be a bit of a tricky one. Let's just put down everything that we know first. So it's a horizontal distance of 5.3 meters. So let's just write that on our picture. So 5.3 meters. We have a distance below the ring. So the ball is going to be traveling from here to here is 1.2 meters. We have a release angle of 48 degrees, so that's going to be this one here. And the whole point of this is we're trying to solve for the initial launch velocity. So let's get to it. What we're going to do is to start with, let's break up our initial launch velocity that we're trying to solve into its component vectors. So if we've got our launch velocity here, we'll call it V0. Our horizontal component of the launch velocity is going to be V0 times the cosine of 48. Cool, because we know that this angle here is 48. They tell us that in the question. Now, what we have to do is then we can say that the horizontal velocity, or the horizontal component of the initial velocity, is going to be V0 times the sine of 48. Cool. So, the trick with this question is to figure out how we're going to relate all of the parts. Now, we know that, well, hopefully you know that in projectile motion questions, the horizontal component of the projectile's velocity is fixed. So in terms of if you ignore wind resistance or air resistance, the horizontal velocity never changes. So we can actually quite easily determine a relationship for the time that it might be in the air for with respect to the initial velocity. So we can start by using the formula S is equal to Vt. S being displacement, velocity being velocity, V being velocity, and T obviously being time. Now what we can do is we can then use that to deduce that time is therefore going to be equal to S over V, which is equal to the distance covered in the horizontal direction, which is 5.3, divided by the velocity in the horizontal direction, which is V0 cosine of 48. Let me just make that a little bit bigger. Cool. So now we saw, and that equals time. So here we have a formula which relates the time that the object's going to spend in the air to its initial velocity. Now what we're going to need to do is we're going to need to come up with some sort of relationship between the horizontal displacement of the ball, in this case, or of the projectile in the general case, and the launch velocity. So what is our final horizontal displacement? Well, it's 1.2 meters. We goes up and then comes back down, and we land it at 1.2 meters above where we shot it from. So what we can do is we know that the displacement is 1.2. We're going to use one of our general equations of motion, which is S equals ut plus 1/2 at squared. Now u is our initial velocity, and that's because this is in our, this was, let me just write this down for you. This here was in our horizontal direction. And this is going to be the vertical component. Cool. So the vertical displacement in this case is going to equal 1.2. The initial launch velocity in the vertical direction is going to be v naught, what we're chasing, sine of 48, times by time. Now we can write time in, or we already have an equation that links time and the initial launch velocity. So we can just put, I would just put that straight in. So let's put this one in brackets just to make it easier to see. And then the time in terms of our initial launch velocity is 5.3 divided by v naught cosine 48. And then what we're going to do is we're going to add 1/2 acceleration, which, because this is in the opposite direction to the launch velocity, or it's going to be negative 9.8 times the time squared. Now we are aware that the time is 5.3 over v naught cosine 48, and we're going to square that. Cool. So now a little insight comes into this where we're able to, because at the moment we've got quite a few v naughts that it's going to make this very, very difficult to solve without like using a graphics calculator or some kind of solving function on a computer. So what we can do is we're going to have a look at this, just this front part first. And we've got this v naught sine 48, 5.3 over v naught cos 48. So let's have a look at that. So if we multiply these two together, we're going to have 5.3 multiplied by v naught sine 48 divided by v naught cosine 48. Now, hopefully from, I don't know, a younger you would understand that these two v naughts are going to cancel out because they're all times, so v naught divided by v naught is just 1, and they will cancel out. And also that the rule is that sine of theta on cos of theta is equal to tan of theta. So we can then just write this entire equation as 5.3 times the tan of 48. So the v naught components have cancelled each other out, and the sine 48 over cos 48 has become a lot neater with just a tan 48 there. So let's go back to blue and keep this equation going. So we're going to have 1.2, and like we just worked out, is equal to 5.3 tan of 48. And then we've got half of negative 9.8 is going to be negative 4.9. And then we've got 5.3 squared, which is 28.09. Divided by v naught squared cos squared 48. Great. Now what we can do now is we can multiply into this bracket from the back. So we can go 4.9 multiplied by 28.09. So let's just rewrite that. It's going to be equal to 5.3 tan of 48 subtract 137.641 divided by v naught squared cos squared 48. Great. Now I hope I don't run out of space. Let me just change colour so you can see where I'm going with this. From here to the end of the problem is basically just algebra. So there's not really too much more physics in it. It's just making sure you get your maths right. So what we're going to do here is I'm going to go 137.641 divided by cosine squared of 48. And I'm going to end up with 1.2 is equal to, let me just write that a little bit higher. 1.2 is equal to 5.3 tan of 48, sorry, minus 307.416 divided by v naught squared. So here, to get that 307.416, I divided 137.641 by cos squared of 48. Okay, so what we can do then is we're going to use a little bit of algebra again. I'm going to remove this entire thing over to the other side. I'm going to move this over to here. I'm going to then multiply by v squared and then divide by that entire thing. And what I'm going to end up with, I'm not going to do every step of my algebra. I'm going to assume that you guys know how that would work, just for space concerns, is going to be equal to 307.416 divided by 5.3 tan of 48 subtract 1.2. Now you guys can do the algebra on these if you like by yourselves and see if you can get from here to there. I guarantee it's the right way to go. So once we've computed this, we then take the square root of it and we find finally that v naught, or the launch velocity out of the basketball player's fingers, is going to be equal to 8.1 meters per second to the -1. So that's our answer right at the bottom. Now this is a relatively complicated projectile motion question. You're not really going to get that much harder than this. The reason for that is because to solve for the launch velocity, or similarly to solve for the launch angle, you'll have to combine the two components together. Like usually what you would do is you would solve the horizontal component and then you would solve the vertical component and then you would add them together at the end to figure out where it's going or how far it's gone or how long it's in the air for, etc, etc, etc. In this one you can't. You have to use the horizontal component to find an equation that relates launch velocity v naught and displacement to find time. Then what you have to do is then you have to find another displacement equation that which also includes the acceleration due to gravity, which is usually, well, always is this s equals ut plus half at squared, We then can sub in the t that we get from the horizontal relationship, and from then, once you've subbed in t, it's just an algebra exercise to solve. So I would have a go at practicing this. The steps for any projectile motion question like this are basically exactly the same. You don't really have to do anything else. So have a practice at these. You can just sub in different angles and different values for the horizontal and vertical distances, and have a go at trying to solve them for yourself. So I hope the video helped. If you liked it, give it a bit of a thumbs up, and be sure to subscribe to my channel. I try to put out new videos most days, and if you have any problems, send them to me and I'll have a go at solving them like this person did here. Alright, thank you for your time. I'll see you again next time.